So this completes the design of the register transfer level custom single purpose processor, right? So we have designed the controller, we have designed the data path. So when we talk about now optimizing the single purpose processors, so we'll look about this particular important thing, which comes under the category of optimizing single purpose processors. So basically, what is optimization? Optimization is the task of making design metric values the best possible, right? So we looked at examples of design metrics, for example, size, power consumption, right, NRE cost, etc. So we want to make those, the values of all those, as best as possible. So basically, what are the areas or opportunities for optimization, right? We can optimize at the level of the original program, which is called algorithmic optimization, right? I can write shortly as the algo. So we can optimize the original C program, original algorithm for an optimization. We can optimize the FSMD that we drew. We could optimize the data path that is there, and we can finally optimize the FSM or the finite state machine, right? So these are basically the opportunities for optimization of single purpose processors. So we'll look at how the steps can be carried out for each of these levels of optimization, right? A single purpose processor might be optimized at one particular level, or a single purpose processor might be optimized at all of these levels. So there are different things we can optimize at each level. For example, in the original program, we could optimize the algorithm. In the FSMD, we could optimize in terms of states. In data path, we could optimize in terms of the functional units. And finally, in the FSM, we could optimize in terms of, for example, how the state encoding is done for our FSM. So let's first look at optimizing the original program. We could analyze the program attributes and look for areas of possible improvement, right? So we can look at the coding of the algorithm and we can see what things can we optimize as far as the algorithm is concerned. So main thing is the number of computations, right? Computations take a lot of time, especially if we have floating point computations. The more computations are there, the more time is consumed by the algorithm. So if we could reduce the computations somehow, we are going to be optimizing the original program. Size of the variable is a very important optimization, and I tell you that this is a small optimization, but it results in a lot of improvement in the original program, right? Size of the floating variable means that calculations involving double precision are very time consuming and slow, and so is the case for floating point computations also. These are also very slow. So the idea is, if we could reduce the size of the variable, right? Double is 64 bits and float is 32 bits. So if you could reduce the size of the variable, for example, if you could carry out the same computation using integers or ints, which are 16-bit values, so our time would increase, because smaller multiplications, divisions or operations between smaller size variables are faster as compared to the mathematical operations on bigger size variables like double or float. So in many types of algorithms, we play with this thing. There is also the concept of fixed point computations. So many of the algorithms, like for example machine learning algorithms or AI inference algorithms, right, when they are run in the inference mode, we many times convert these demanding double precision or floating point computations into the fixed point computations. And when we convert into the fixed point computations, the complexity of the circuits decrease considerably, And this is, I am talking from the point of view of FPGA implementations as well. In addition to that, the time to completion of the algorithm decreases, because the speed of the algorithm increases. So as far as optimizing the original program is concerned, you could also think in terms of time and space complexity. So what is basically time and space complexity? Right, we discussed this in data structures preliminary courses, right? Time and space complexity means we can trade off time for space. We could give an algorithm more space to reduce the time of operation of the algorithm. So this is basically a trade-off. Space is increasing and as a result time is decreasing. And also we could optimize in terms of operation used. Multiplication and division are very expensive, right? So if we have to multiply by 2, we could replace it with a shift operation, shift left operation. Remember our discussion of the microprocessor course. Also, for example, we have to divide by 2. Again, we can convert it into the shift right operation. Shift left and shift right are very fast operations as compared to multiplication and division. So it's an excellent optimization we could do. Let's look at an example to understand the optimization using this technique, right? Now this is a program, right, which is the greatest common divisor, or GCD. So let's try to run this program for a set of values to find the number of iterations. So let's say we have the values of 42 and 8, right? So we have this first iteration, right? This is understood, so we go out over here. So basically in the first iteration, x equals 42 and y equals 8. Definitely x is not equal to y because 42 is not equal to 8, so this is true. Is x less than y? No, because x is greater than y. So x is x minus y. So after the first iteration, what becomes the value of x? X becomes 42 minus 8, or 34 comma 8. So this is the after the first iteration we got this value 34 comma 8. Now when we iterate for 34 comma 8, again this is true and again this is false, so we again execute this, right? So it is 34 minus 8, right? And 34 minus 8 comes out to be 26 comma 8. So please carry this out and let me know the total number of iterations, right? So when we carry this out, the total number of iterations come down to be 9, right? First iteration was 42 comma 8, then 34 comma 8, 26 comma 8, 18 comma 8, 10 comma 8, 2 comma 8, 2 comma 6, 2 comma 4 and 2 comma 2. Now after having discussed that, let's try to move to the right hand algorithm, right? So this is basically an optimized program that we are having, right? So let's try to run the same run it with the same values, right? 42 comma 8. Is x underscore I greater than or equal to y underscore I? Yes, x is greater than y, xi and is greater than yi. So we assign xi to x and yi to y. The first iteration is 42 comma 8. So now while y is not equal to 0, what do you do? R is x modulo y. So R is 42 modulo 8 and R comes out to be 2, right? So what do? We assign y to x. So x equals 8 and y equals 2. So the answer that we have now is 8, 2. So this is now this would carry out the second iteration, right? So 8, 2, again, yes, x is greater than y, so x is 8 and y is 2. Again, y is not equal to 0, so we'll compute, right? R is 8 modulo 2, which comes out to be 0, right? So x equals 2 and y equals 0. So we have this 2, 0. So of course this is true, so we'll do that. We'll come over here, but of course now y is 0, so we want to execute this. This is going to be the value of 2. It's going to be our answer. So how many iterations? 1, 2 and 3. So 9 iterations for this version and 3 iterations for this version. So based on iterations alone, this optimized program is better than the original program. After the analysis of the first step, that is basically the first level of optimization, which is optimizing the original program, we can move on to the next level of optimization, which is basically optimizing the FSMD. What was the FSMD? FSMD was the figure we drew previously, right? And we can recall that this was basically the FSMD, right? And neatly drawn, this one was the FSMD, okay? So let's look at how we can optimize the FSMD. So when we are optimizing the FSMD, we can look at areas of possible improvements. And one of the areas of possible improvements is to merge states. And what do we mean by that? States with constants on transitions can be eliminated because transition taken is already known, right? While one is one such loop, right, that can be merged. We'll see. And also states with independent operations can be merged. So if our states contain independent operations, we would be able to merge them, right? So for example, if one of the states says x equals x underscore I and the other state says y equals y underscore I. So based on the data path operations, right, are these two states related in any way? That is state 3 and state 4 in the FSM that we drew earlier. So we see that these are separate control signals. X select and X load takes care of loading the variable X, and Y underscore select and Y underscore load takes care of loading the variable Y. So independent control signals. So we don't need to have two states to carry out these operations. Both operations 3 and 4 can be carried out in the same state. In other words, states 3 and 4 can be merged. We can also separate states. For example, states which require complex operations, A multiplied by B multiplied by C multiplied by D, can be broken into smaller states. For example, A multiplied by B can be carried out in one state. C multiplied by D carried out in another state, and this product multiplied by this product can be carried out in a separate state. So what would be the benefit of separating the states? We would be able to reduce the hardware size. Why? Because we are reducing the complexity. Then also we could take help from scheduling, right? For example, if we have one multiplier can be scheduled for A multiplied by B in one state, and that same multiplier can be scheduled to carrying out C into D, and finally this same multiplier could be used to carrying out the product of A multiplied by B computed earlier multiplied by C multiplied by D computed earlier. So these are basically the possible areas of improvements that we could have. So let's look at basically optimizing the FSMD, right? So I would invite you all students to please look at your original FSMD that you drew, right? So basically, what is the first state? While one loop, yes or no? So while one, of course, can be eliminated. State 1 can be eliminated because we already know that this is true, and we will move on to state 2. So instead of going to state 1 and then going to state 2, we could directly start with state 2. Then of course we could merge states 2 and state 2j. Why? Because there was no body of the loop between 2 and 2j. What was 2 and 2j? G0 underscore I loop. So we could merge these two. So after the first optimization we have single state 2. Then of course we have the state 3 and 4 which are merged into state 3. Then of course we could merge state 5 and state 6. Why? Because in 5 we check x is not equal to y, and then in 6 we checked x is less than y and not x is less than y. So there is no need basically for this state x is not equal to y, because later on we are having the discussion of x is less than y or not x is less than y. So of course if both of these are not true, it would mean that state 5 is false, and we can directly move to state 5j and 6j. So what do? We merge states 5 and 6 into a single state, and we carry out two operations: x is less than y and x is greater than y. So if x is less than y, what do? We go to state 7, y equals y minus x. It remains as it is. And if x is greater than y or not x is less than y, we move to state number 8. Now in either case, when we move from state 6 to state 7 or from state 6 to state 8, we don't need to go to state 6j, we don't need to go to state 5j. We can directly move from state 7 to state 5. Similarly, we could move directly from state 8 to state 5. So what do? We eliminate 5j and we eliminate 6j. So what do we get? From state 7 we move to state 5, and from state 8 again we move to state 5. So if state 5 is false, what do? We go to state 9. So from state 5 directly we go to state 9. And now since state 1 has been eliminated, we also eliminate state 1j. So if 5 is false, we move to state 9, display the output, and from state 9 we directly move again to state 2. So this is an optimized FSMD because it contains a much less number of states as compared to the original FSMD from which we started. So the figure on the right hand side shows us the optimized FSMD, which contains really less number of states, right? So less number of states means small size of a state register and small logic. So it would basically represent an optimization. Now let's look at how we can optimize the data path. data path can be optimized by sharing of functional units. Previously we had one-to-one mapping, remember? We had two subtractors to carry out x minus y and y minus x. But this may not be necessary. If the same operation occurs in different states, they can share a single functional unit. For example, if one state is carried out x minus y and the other state carries out y minus x, so we might have the same subtractor. In the first state, that subtractor would carry out x minus y, and in the next state the same subtractor can carry out y minus x. Or the multiplication example that I showed you earlier on, right? We could have a single multiplier which would carry it out in one state a multiplied by b, and the other state c multiplied by d, and finally in the third state multiplication of the products ab and cd. We can also have multifunctional units, or the concept of ALUs, arithmetic and logic operations. Since they support a variety of operations, it can be shared among operations occurring in different states. But again, if we have these kinds of ALUs, we are moving away from the spirit of the SPP or the single purpose processor. Now we move on to how we can optimize the FSM or the finite state machine. We can do this by state encoding. And what is state encoding?